So this is your recent work.
I'm sorry, sir.
Oh, this is your recent work.
Yeah.
I thought it was
Yes,
your
yes.
old work with Sanjay.
It is the recent work with Michael.
We can start.
You can start. Yeah, welcome to the APRG seminar this week. So today we have Tapendu Rana from Ghent University, and he'll give a talk on pseudo-differential operators on radial sections of line bundles over the Poincaré upper half space. Tapendu.
Thank you, Professor, for the introduction, and thank the organizer for giving me this opportunity to present my work here. So today I will start with as the known space, Euclidean space. There we'll study the multiplier operators and series operators there, and rough symbol class for series operators. And then we'll move on to this space with exponential volume growth, for example, the Riemann symmetric space, and discuss what are the results are there. And then we'll take a brief introduction of dependent theory on SL2R and Fourier transform, variation of Fourier transform on SL2R. And using this Fourier transform, we define multipliers for fixed K types on SL2R. And then we state our results of series operators there. And finally, we'll end our talk by giving the idea of the proof. Okay, so in Euclidean space, this is very well known. You can take a nice enough function and define its Fourier transform. And this is your inversion formula. And we also have this Planck-Shelford theorem. It says for all L2 functions, the norm of Fourier transform and the function itself are same. Okay, now one of the fundamental problem in the harmonic analysis is that boundedness of multiplier theorem. To be explicit, suppose you define a multiplier operator TMFX. This is the inversion formula where this is M is the multiplier of the operator Tm. Now you ask this when such operators is bounded. Okay. Now if you take a bounded function, then you have this Planck-Shelford theorem, which immediately gives you that Tm is L2 bounded. If you assume M is bounded. Now what about P not equal to 2? What can we impose on the multiplier M so that the associated multiplier operator is LP bounded? One such condition is the Hall-Mendel differential inequalities. If we assume that the multiplier satisfies these differential inequalities, then the operator is LP bounded for P belongs to 1 to infinity. Now, I like to mention that here M is allowed, derivatives of M is allowed to have singularity as I equal to 0. Okay, so even if we assume this derivatives of multiplier at singularity as I equal to 0, then Tm is LP bounded. Now, to make our life more complex, one can ask that what if you replace this multiplus with a more general symbol? For example, if you take a differential operator pxt like this, then you can represent that in the following way, where this symbol not only depends on xi, but as well as x. In fact, for a more general function, xi on Rn cross Rn, one can consider the associated sequence operator defined in the following way. Here also, we can ask that what condition can you impose on M, impose on A so that the associated sequence operator is LP bounded. Okay, and to study this boundedness properties of sequence operator, Hall-Mendel introduced this symbol class SM dot delta, which consists of smooth functions satisfying these differential inequalities. Okay. Now, it is well known that if you take a symbol from the symbol class S010, then the associated sequence operator AXT is bounded from LPRN to itself for 1 less than P less than infinity. And I would like to remark that unlike in Hall-Mendel multiplier theorem, if you allow the derivatives of symbol AXI have singularity at xi equal to 0, then the corresponding operator may not be bounded. Now, it is also well known that if you take a symbol from the class S010, then the associated sequence operator is actually belong in the realm of Calderon-Zimmermann operator, where the smoothness condition with respect to the space variable is crucial. Now, this raises the question that
So Tapendu, operator may not be bounded means where to where you are taking?
If you take this, especially there, we can construct a symbol which satisfies this condition, where the operator is not L2 to L2 bounded. It can be shown. It is in the Stein box there.
Oh, okay. And this theorem is not including 1 and infinity, right? Only
Which theorem?
for Stein's theorem, 93.
This theorem is, there may be other symbol classes where for a particular symbol you can construct where it is LP bounded, but it is for this kind of symbol class, this can be proved using the Calden-Zygmunt theory. It is done in the Stein book.
No, I am saying that it is bounded in LP for 1 less than P less than infinity. But at endpoints, it is not bounded, right? This theorem? Means L1 to L1.
For P equal to 1 case, this is weak type 1.
Weak type 1, okay.
Okay.
P is equal to infinity? No, nothing is there.
Not known. I'm not sure it's known there. Okay. May I continue, Mother?
Yeah.
Okay. So as I was saying, so if we take a symbol from this class H010, this belongs to a more generalized operator, Calden-Zygmunt operator, where the smoothness condition with the space variable is very crucial. So this raises the question that what if you want to restrict the smoothness condition on the space variable and still want to study this boundedness property of this Hüll's operator? And in this direction, many authors, for Kumanogo, Hormander, Negache, and Kaufman-Meyer, they actually contributed to this LP boundedness problem with limited regularity on the space variable. More recently, in 2007, Koenig and Stauber studied this LP bounded of Hüll's operators with non-regular symbol. They introduced this rough symbol class, which consists all symbols which smooth with respect to the space or dual variable, but it doesn't need to assume any regularity symbol with the space variable. Okay, so SM rho infinity containing all these symbols which satisfying these inequalities. Then they showed that if we assume m less than n into rho minus 1 by 2, and then AX3 is a bound operator from LP Rn to itself for P belongs to 2, infinity, and if we take rho equal to 1, then for all m less than 0, the range of P varies from 1 to infinity. Okay, but still they use this very much the doubling volume property of the equivalent space. But there are spaces, for example, Riemann symmetric space, where this doubling condition doesn't hold because of this extensive volume growth property of the Riemann symmetric space. Okay.
Can I go back to the last result? Yes. Yeah.
Okay. All right. So without going any technicalities, let me introduce Riemann symmetric space in this way that suppose G be a non-compact connected semi-simple group with finite center. We can take, for example, G equal to SL2R and K be a maximal compact subgroup. Then the associated Riemann symmetric space non-compact type is X equal to G quotient by K. Then this group G has this Eva-Stein pattern decomposition, which written like G equal to K AN, where this K part actually is coming from the compact part of G, and this A is the abelian part of G, and N is the nilpotent part of G. We also have this pattern decomposition, and since this decomposition is unique, we can define this function HG, which simply saying that for each G, we denote HG is the projection of G on the eighth component of G. And similarly, G plus from A plus component of G. And we can write using the Iwasa decomposition and Cartan decomposition in the following term. And using this H function, we define this capital A function from x cross K to A, defined like this. And now to define this Helgason Fourier transform, we will do the exactly same way what we did in the Euclidean setting. We simply integrate the function, the integral function against the all eigenfunction of the Laplacian. Here, the eigenfunction of Laplacian are exactly of this form, as E lambda kx. Okay, so for a L1 function on symmetric space, we define the Helgason Fourier transform by integrating the function fx against this E lambda kx, which is the eigenfunction of the Laplacian. And interestingly, if we take a k radial function or k variant function, that is which doesn't all functions which doesn't change its value, if you act the k on x or left or right, it doesn't change its value. We say such function as k variant function, And for such k-variant functions, the Helgason Fourier transform reduced to the spherical transform, where this phi lambda is called the horizontal spherical function of the symmetric space X.
So you are taking the rank one spaces, right?
I am taking
from the beginning. Rank one spaces from the beginning.
Yeah,
right?
yeah, okay, yeah.
But you
Yeah,
didn't mention something. I think that
I haven't used anything on rank one. Yeah, so here I need to mention that
because
in the
lambda
rank
is
one case,
because
yeah.
lambda you
So
are taking
in this talk, forget. I'm sorry, in this talk we'll stick to the rank one symmetric space for in this talk, and to avoid technical notation and our talk will be based on the rank one symmetric space. Rank one means here this Lie algebra of this abelian group is dimension of the Lie algebra of this abelian group is 1. Okay. I was going to mention it later. Okay, sorry. Yeah. So for this Helgason Fourier transform, the inverse Fourier formula reads as follows: is in this way. So now that we have inversion formula, using this we can define the multiply operator in the following way. And if you take a multiply is bounded, then using we also have this Planchel formula here. Then using Planchel formula, Tm is L2 bounded. Okay. Now, coming to the question of P not equal to 2 case, the boundedness Tm for LP bounded for P not equal to 2 case. So let us remind ourselves that this space exhibit exponential volume growth. So before you ask that what condition can you put on M so that the Tm is LP bounded, let us ask that what should be the necessary condition on M so that the Tm is to be LP bounded operator on X. Okay, and this work actually initiated by the Clarkenstein in 1974, but they realized that in this setting of non-compact type symmetric spaces, a strong necessary condition needed due to the holomorphic extension power of the Fourier transform of LPX functions. And then in fact they showed, suppose M be a bounded measured function on R, and suppose that the associated operator Tm on L2x extends as a bounded operator on LPX for some 1 less than P less than 2, then M extends to as a holomorphic function on the interior of the strip SP and is bounded there. So SP means this strip, where rho P is mod of 2 by P minus 1 rho, where rho is a constant depending on the symmetric space X. Okay, so here the holomorphicity condition on SP is absolutely necessary. Later in 1990.
So I have a small question here. So yeah, inside the interior of the strip, it is holomorphic.
Yes.
But it can be, I think, continuously extended to the boundary itself.
No, can be means what? We're talking about necessary condition. So
yeah,
it
M extends as a holomorphic function in the interior of SP.
No, it is not necessary that it has to be extended to a holomorphic on the boundary. Only necessary is that.
No, you are not getting my question. I am saying that it is it continuous in the boundary?
It doesn't say anything on this.
I think this uniformly bounded thing will give that.
Yeah.
Okay, you can.
You can surely say that the derivatives of this multiplier may not be extended continuously on this boundary. So I'll come to that when I mention this Ionescu result.
Yeah.
Okay. So later in 1990, Anker proved an analog of Hermann-Melian multiplier theorem on non-compact type symmetric spaces, where he showed that if the multiplier satisfies this kind of differential inequalities, then the associated multiplier operator is boundary operator on LPX. And now, if you recall this Hermann-Melian multiplier theorem on Rn, which says that if M satisfies this kind of differential inequalities, then the multiplier operator is LP bounded. And here, in the Euclidean setting, the derivatives of M allowed the singularity as I equal to 0. But for technical difficulties, Anker assumed this regularity condition where the derivatives of M are not allowed to singularity at the boundary of SP. But if we mention that this.
Tapendu, can you repeat this point? I could not get this.
So in the setting of Rn, so if multiply satisfy this kind of condition, where the derivatives of m allowed to have singularity at xi equal to 0, still then in the equivalent setting, the Tm is LP bounded. But
Yes.
here, if you observe this anchor condition on the multiplier, here you cannot allow the derivatives of m have singularity at any points upon SP. Okay.
Yeah.
But anchor still actually mentioned this in this paper that it should be allowed to, in fact, it is allowed to relax the singularity condition of derivatives of m and still m to be a bounded operator in LPX. And this exact question was followed by Ionescu, where you assumed that if you take a multiplier satisfy this kind of differential inequalities. Now here observe the derivatives of m have singularity at plus minus I rho p. Okay, here rho p is these 2 points. This is plus I rho p and this is minus I rho p. Okay, so Ionescu showed that if you assume that m derivatives of m satisfy this kind of inequalities, that means the derivatives of m has singularity as plus minus I rho p, the boundary of SP. Still, then the associated multiplier operator is a boundary operator in LPX. Okay, and later, inspired by these results of Ionescu and Anker, Ricci and Robel focused on the group SL2R and started this LB-honest property of multiplier operators there for fixed K time. But before that, we would like to go, discuss some of the representation theory on SL2R. All right. Okay, so let me
just
recall that.
Last point. Okay. Yes.
Okay. So let me recall. The group G equal to SL2R has the following Iwasa decomposition. G can be written as Kn, and there is another decomposition. Iwasa decomposition is converted N bar K, where K equal to SO2 group, and A is this abelian group containing all such matrices, and the nilpotent group is called containing all such matrices Nzi of this form. And for N bar K, this is your N bar containing all such matrices of N bar Xi of this form, and you can write K equal to SO2 as the K theta containing all matrices of this. Now, by the Iwasa decomposition, for any x belongs to G, it can be uniquely written as x equal to K theta, AT, and Xi. And for using this, we define Kx equal to K theta and Hx equal to T. That means we're taking this function, we're projecting x on the kth coordinate, and this H function projecting x on the A coordinate. And we say that a function on G is a left or right K type n if you can bring out this K by multiplying this ENK factor on this side. What is ENK? ENK is defined like this. ENK theta equal to IN theta. For example, if you take n equal to 0, this actually your radial function on G. Okay. And for a class of function f on G, we'll simply denote fmn, which are left m type and right type n. Right. Now, to define principal series representation, let me say m equal to plus minus identity, the group plus containing plus minus identity, and m hat the irreducible representation of m containing tau plus and tau minus. Tau plus defined like this, and tau minus defined like this. And for tau equal to tau plus, we will denote zeta as the set of even integers, and tau equal to tau minus, that is denote the set of odd integers. And now for tau belongs to m hat, we define h tau to be the subset of L to K containing generated by the orthonormal set En belongs to n z tau. For tau belongs to m hat and lambda belongs to C, we define this principal series representation pi tau lambda, which is from h tau to h tau, and defined like this. Pi tau lambda x En at the point K is equal to I lambda minus 1 h of xk, and En of this form. For K, I recall K is this function. K is equal to K theta. Okay. For principal series representation, we define the canonical matrix coefficient of the principal series. I define as usual. We're taking the inner product of pi tau lambda x em with En and denoting as pi m and tau lambda x. For all tau belongs to m and lambda belongs to C. And here also in the group setting, we have this discrete series representation. That is, for k belongs to Z star, there are representation pi I k h k of G are discrete series representation. And canonically, we can define the canonical matrix coefficient of discrete series psi ln I k x, pi I k x, e n k e l k. And for k belongs to Z star and ln belongs to ZK is defined like this. And for pi tau minus 0, it has two irreducible representation, so-called Mach series, is denoted by d plus and d minus. And the representations of d plus and d minus contain en belongs to L2k, respectively for positive orders and negative orders. Here I like to mention that in my paper, usually the representation theory on SL2R, which I followed from the Barker, in the notation of Barker, the unitary dual of SL2R is the imaginary line and non-negative integers. But according to my notation, I change the parametrization so that my unitary duals become the real line and the integers on the imaginary line. Okay. So
what is pi ik? Means I is there. I think pi k h k, right? What is I here?
Not exactly. So pi I actually, if we what discrete representation comes from if we take k belongs to Z star, this pi tau. So suppose if you take k as an integer and k is an odd integer and pi tau plus comma k, it's actually become a reducible representation. And from that, we can get another representation called discrete series representation, which will be reducible and sort of this matrix coefficient of this discrete series representation has a relation with spin series representation. In particular, if you take L equal to n, this psi I k ln is same as pi I k ln. This one. Okay, but these are not important for my talk. Basically, you can assume you can assume there are some discrete series representation and there is spin series representation. For details, you can follow the Barker's book because I don't want to go to the
actually, I have
details.
forgotten it. Anyway, I've seen this thing.
Yeah, this is a bit technical. That's why I want to avoid it quickly.
No, that's okay.
Okay. So since we're in a group setting, suppose we want to take a compactly sorted smooth functions, then the spin series Fourier transform FH hat is a actually operator from m hat cross r to bh star defined like this. That fh tau lambda equal to integration over fx pi tau lambda x inverse dx. This is defined as usual in the weak sense. And similarly, we define the discrete series Fourier transform is the operator fb hat from iz star to union of bhk, k belongs to z star, which defined as similar as in the case of principal series representation. Okay. Now, interestingly, if we take a n-type function instead of a general function on G, then the principal series Fourier transform reduced to this scalar valued Fourier transform in the following sense that if we take n-type function, all the coefficient of the operator fh tau lambda is zero except this nth coefficients. So if you take n equal to L or L not equal to n, this matrix coefficient of this operator was 0. So that's why in this sense, the Fourier transform reduced to the scalar value Fourier transform. Same happens in the case of discrete series Fourier transform. If you take a n-type function, then for k belongs to gamma n, only this kind of Fourier transform survives. All the others discrete series Fourier transform is 0. And now, I like to make a remark that all that we are talking about, all this Fourier transform, actually branch of the same tree. In fact, if you take a Helgason Fourier, you can obtain Helgason Fourier transform from the spin series Fourier transform. Like, so if you take a right k-variant function, all your discrete series Fourier transform vanishes, and you can obtain this Helgason Fourier transform in the following way from the spin series Fourier transform. That is, f tilde lambda k can be defined as fh tau plus lambda e naught acting at the point and getting at the point k. And if you put explicitly the expression of pi tau tau plus lambda x inverse, you will get back your Helgason Fourier transform. Okay, now coming back to this n type functions. So we have this inversion formula for n type function on G, which reads as follows. Now, unlike in symmetric space, we also have this discrete part of this inversion formula here. Okay. Now, using the inversion formula, we can define this multiply operator for n type functions. Okay, and Ricci and Rogel observed is that even in this setting, this holomorphicity and boundedness property is essential to study this LP boundedness property of Tm. Okay. In fact, they proved that suppose P greater than 1 and less than infinity and P not equal to 2, and assume that the multiplier M from SP union I gamma n to C is a function such that M is a bounded even holomorphic function SP naught, and del alpha del lambda alpha extends continuously to SP and satisfy this kind of inequalities for all alpha from 0.2. Then the corresponding Fourier multiplier operator Tm is a bounded on LPGN. What we are asking that what if we replace by the multiplier by a symbol sigma x lambda and study the associated Sylun's operators, the LPGN boundedness properties. So formally, let me define Sylun's operator. So for a pseudo function sigma from G cross R union I gamma n to C, we define the associated Sylun's operator for any type function on G in the following way. Okay. We denote this continuous part as psi sigma con and discrete part as the same way. And now, before we state our results, let me give introduce some more notation for Harmonic norm for symbols. Order JK. So suppose sigma from R cross U to C, U is an open set in C, where it is for each x belongs to R, sigma x lambda is a holomorphic there, and we define this symbol class of harmonic symbol class of order JK. What it means is that if we take derivative with respect to lambda variable, then you get a more decay with respect to lambda towards infinity. And if we take the derivative with respect to s variable, it is becoming, we can bound this by a constant, just like the S010 class in the classical setting. Assuming this, so we prove the following theorem. That suppose P belongs to 1, infinity and P not equal to 2.
Go back to last. Okay.
Okay.
Yes.
So, but P belongs to 1 infinity and P not equal to 2, and suppose that sigma from G cross S P union I gamma into C is a function satisfying these two conditions, and for each V bar belongs to N bar, where N bar is a group, the nilpotent element of the group SL2R. The function S lambda goes to sigma V bar S lambda, defined like this, belongs to the H of SP22. It means that the norm of this symbol is finite, and moreover, supreme over V bar belongs to all such symbols. The Harmonic norm of order 2 is finite. Then psi sigma extends to bounded operator from LPGN to itself. Okay. All right. So this is one of the main results, and now we'll be bit more technical to discuss the idea of the proof.
Do you have to assume that sigma is k by n variant?
Yeah, you can assume sigma is other k type, but then it won't be so in this operator. If you define process, if you take any other, suppose take ln type, then since the spherical function is of nn type, so it will add the type of sigma it is. So since we are interested in the LPG nn boundedness, we assume sigma to be a by k by invariant. But if you take suppose sigma LM type, then you will get some other properties, like instead of LPGNN to itself, there will be LPG LM. But the analysis will work in the same way.
Oh.
But it's a nice observation. Thank you. All right. Okay, so now to study this boundedness property of psi sigma of x, first let us recall that we can write as a as two parts, as continuous parts and a discrete parts, and each of these operators requires a different analysis to prove their boundedness. And in the case of multiplus setting, what Ricci and Rubel actually use the fact that you can write the multiplier operator as a convolution operator. And in this semi-simple Lie group setting, we have this amazing Wingenstein phenomena, which help use to which can be help to get a estimate of a convolution operator. And more explicitly, they use this fact of discrete Fourier transform, discrete matrix coefficient that we said that if we take a 0 less than p less than equal to 2 and gamma p equal to 2 by p minus 1, then mod k greater than equal to gamma p if and only if psi belongs to LPG, where psi is a k finite matrix coefficient of pi I k. And they use this and the convolution, the Wingenstein phenomena to get the boundedness property of the discrete part of the multiplier operator. But in this Sirun's operator case, we are also interested in the weak type 1 estimates of this discrete part of Sirun's operator. So that forced us to investigate some of the representation theoretic problem in the case of SL2R. And particularly, we were interested in the case, what happens at mod k equal to gamma p. What can you say about the representation matrix coefficient of the discrete Fourier transform? In fact, we proved this weak type version of the Minkowski result in the case of SL2R that if we take 0 less than p less than equal to 2 and gamma p equal to 2 by p minus 1, then mod k greater than equal to gamma p if and only if psi I k n belongs to LP infinity G. In fact, if we take mod k equal to gamma p, then we prove that psi I k n belongs to LPQG if and only if q equal to infinity. That is, it won't belong to LPQ for any q less than infinity. And you can replace this n with any m not equal to n. Still, this result holds. And isn't this and sharp estimate of this matrix coefficient of discrete series? We prove that independently if we take the discrete part of the epsilon over psi sigma and assume this symbol satisfies this condition, then the discrete part of Sirun's operator is bounded from LPGNN to itself for all p belongs to 1, infinity. Okay. All p belongs to 1, infinity, and for p equal to 1 case, we have to be careful that for p equal to 1, if n belongs to z tau minus, that is tau minus z tau minus containing all odd integers, then psi sigma, discrete part of psi sigma is a bounded operator from L1 GNN to itself. And if n equal to z tau minus z tau plus, that is set of all even integers, this psi sigma is a boundary operator from L1 GNN to L1 infinity GNN. And for this part, we use the results of this operator, of this lemma. Okay. Now this settles the analysis for the psi sigma of discrete part of the psi sigma. Now, to handle this analysis of continuous part of psi sigma, we had to consider the fact that this upper half plane constitute exponential volume growth. For this, we first write down the continuous part of this Sirun's operator as a common integral operator, which you can easily do by replacing the Fourier transform of f had at the lambda and using the some functional identity of spherical functions. You can write this continuous part of psi sigma as the integral operator, integration over fy k con xy dy, where k con xy equal to defined like this. Now, to take care of this exponential volume growth, we further decompose this continuous part of Sirun's operator in two parts as integration over fy eta naught y inverse x and integration of fy eta y inverse x k con xy dy, where eta naught is a k-variant function supported near the identity and eta is a k-variant function supported away from the identity. And yeah, so we call this part is the local part of this operator, and we call this the global part of this operator. And these two operators require different treatment to study this boundedness property of this. And okay, so in fact, to study this local part of the Schulz operator, what we did is that we first used the integral formula of Cartan decomposition to dominate the LP norm of psi sigma log f and the following by this operator. And now realize that since eta is a k-variant function supported near the identity, so this is basically saying is that we can reduce this operator as a operator in the Euclidean setting. And to do that, actually, there is this transference principle by Kaufman-Weiss, which helps you to transference the operator from on G to the operator in R. To be explicit, if we define this Kaufman-Weiss kernel in this following way, that Kaufman-Weiss kernel xy at T, we define like this. Then, using Kaufman-Weiss principle, we can prove that if this Kaufman-Weiss kernel satisfies this inequality for all H belongs to LPR, then we have this psi sigma log is LP bounded on G. So what is this Kaufman or this lemma we prove using Kaufman-Weiss transform principle is helping doing this is that to analysis of boundedness property of psi sigma log is reduced to the study of this integral operator, this TCW on the Euclidean setting. So now, since we are all in Euclidean setting, we can use the Euclidean theory of Schulz operator to study this, to prove this inequality of this boundedness property. Okay, now, so we're convinced that we now want to study this integral operator whose kernel is the Kaufman-Weiss kernel. Where you recall this Kaufman-Weiss kernel, you can explicitly write using the formula of continuous part kernel of the continuous part of Schulz operator psi sigma, and then you can write Kaufman-Weiss kernel in the following way. Now, here, another acute observation is that if you since eta naught is a compact supported function near the identity, and this eta naught at is the same variable as of the spherical function variable, you can use the decomposition of spherical function to write this integral in a more further and simple in terms of simple functions. To be more explicit, we can write phi n and tau lambda at as in the following way, where this JJ is a generalized Bessel functions, okay, and BJT is a bounded function on T. Then, if you plug in this expansion of spherical function phi n and at in the Kaufman-Weiss kernel, you can write this Kaufman-Weiss as two parts, K0 and the K error part of this Kaufman-Weiss kernel. For K0 XAST, you can write it like this. And this error part of this Kaufman-Weiss kernel, you can handle it very well in the following sense that you can get a integral function kappa, where you can dominate this K error of x at by this kappa, where kappa doesn't depend on x. Now, since K belongs to L on R, you can easily see if you put in KCW is replace KCW by a K error part, then this inequality obviously satisfied, because then this part is getting vanished. And you can see since kappa is a Elon function, this kappa satisfying this inequality. Now, our analysis is reduced to the case to study of kappa 0 XAST. Okay, and for that, what we did is that since we are in an Euclidean setting, we find out what is the Fourier transform of this variable k0 with respect to t variable. So see here we're integrating e to the minus 2 pi I xi t against k0 x sat. So we're basically taking the Fourier transform of k0 x with respect to t variable. And then we prove that this symbol, the symbol means this part. Symbols actually satisfying actually behaving like a S010 symbol class. And thus, using the equilibrium theory of Sirun's operator, we reduce that this K0 and Kr actually satisfying this satisfying this inequality that we mentioned before. And this settled the problem, the LP oneness of the psi sigma loop in the group setting LP. Okay. In fact, for local part of Sirun's operator, we can define this. For local part of Sirun's operator, we can state the following theorem. That if we assume sigma from G cross R to C, we have function satisfying the following properties. And for each V bar belongs to N bar, the function S lambda goes to sigma X lambda is a symbol belonging to HR, 2, and satisfy this inequality. Then for 1 less than P less than infinity, the psi sigma loop is a bounded operator from LPGNN to itself. Now, we observe that here we only using the properties of using the smoothness property on R. That is, we are taking the regularity properties of this symbol or the dual variable in the R setting, not on the full strip SP. In fact, it is required only to handle the global part of the Sirun's operator, for which this statement can be proved. That is, if we assume sigma is a function from G cross SP to C, satisfying the following properties: K variable function on G for each lambda belongs to SP naught, and for each X belongs to G, lambda goes to sigma X lambda is an even holomorphic function on SP naught and satisfy these inequalities. Now here, unlike in the local part, we don't require any smoothness condition on the space variable. So for the local part, we need derivatives condition on the real line only, but also on the space variable. But the global part, we need derivatives condition on the dual variable, but on the full strip. But we don't need any smoothness condition on the space variable for the global part. And for addition with P equal to 1 and N belongs to Z tau plus 1 0, if we assume del lambda alpha has 0 at lambda equal to y, for all alpha belongs to 0, 1, 2, then psi sigma, the global part of psi sigma is the boundary operator from LPGNN to itself. So this condition may seem to you a bit technical, but this actually requires to handle the C function, which is required to study the analysis of the global part. Explicitly, if we take N belongs to Z tau plus, then CNN, this CNN minus lambda function, lambda goes to CNN minus lambda inverse, has a singularity at lambda equal to I. So to handle that, we require this condition. But nonetheless, if you take N belongs to Z tau minus, this you don't need under this condition at all. Okay. Now, to study this boundedness property of global part, what we did is we followed some sort of, in some sense, a classical case. Since our psi sigma global effects can be written as an integral kernel operator of this, where this global kernel is written like eta y inverse x, where eta is a k-variant function supported away from the identity, and eta y inverse is same variable of the spherical functions, and thus we can use this Harishon spherical function of Harishon expansion of spherical function phi n and tau lambda at, which it says it can be for t greater than equal to 1 by 10, or you can take t greater than equal to epsilon or not for any epsilon greater than 0. Then you can write this phi n and tau lambda at like this, where this function is satisfy the following inequality. Okay, I like to mention that this expansion holds for any t belongs to R, but to have this kind of estimates of A lambda t, you need t away from 0. But this expansion will always hold. Nonetheless, what matters what t is from. And this will hold for all lambda with 0 less than equal to imaginary lambda less than equal to 1 plus 1 by 10. Okay, and then using this spherical, using this expansion of the spherical functions and plugging it over here, we can get the estimate of the global part, kernel of the global part, in the following way: that for 1 less than equal to p less than 2, we have the following estimates of the spherical, following estimate of the kernel. And this part is crucial here. This is e2 minus 2 by p y inverse x plus, where y inverse x plus is denoting the a plus component of the in the Cartan decomposition. All right, and to get this estimate, what we did is that we plug in the spherical functions expansion on the kernel expression, and then you can see. So from that, so this is your I lambda t, and this is the minus t, and from that you will get back this e to the minus y inverse x plus, and this is your I lambda y inverse x plus d lambda, and there are also other terms. We can forget about that for the time being. Now we are prepared to use this holomorphic property of the symbol. Next, what we did is that we move the integration with respect to lambda from this line r to a very close line I gamma p, that is from r to r plus I gamma p minus gamma p by 2 y inverse x. So whenever y inverse x plus getting very large, will be very close to I gamma p, but we may not touch it even for any y inverse x plus. And if you move that, but you get this e to the minus y inverse x plus, actually you'll get the minus 2 by p y inverse x plus. So now we're getting more decay using the holomorphic property of the symbol here. And now we can use the integration by parts to get the derivative on this part, and one can usually prove that and the hypothesis that this sigma by CNN tau minus lambda, this term has very nice decay properties. And from that, you can prove that the global part of this kernel satisfies this kind of estimates. And for p greater than 2, I get the similar but not exactly same. Instead of minus 2 by p here, we'll get minus 2 by p prime. It is natural because if you take p greater than 2, 2 by p will be less than 1. So that is not very useful in this case. So eventually the analysis will be same. But since by definition, gamma p equal to gamma p prime for p greater than 2. So using the same calculation as before, you can prove the estimate of global part of this kernel. Okay. All right. Okay. To sum up, the calculation of continuous part of the Shilin software psi sigma is that we started with the symbol, we satisfy these two smooth with these inequalities, and then we decompose the psi sigma in two parts. One is a local part, psi sigma low, which is supported near the diagonal, and another on the global part, which is supported away from the diagonal. For this away from the diagonal, we use holomorphicity of sigma on the dual variable on SP0 to get an exponential decay. And for the local part, we establish a connection with this Euclidean filter operator and reduce the boundedness property of psi sigma look from the Euclidean theory of filter operator. Furthermore, this relation with this Euclidean filter operator actually help us to utilize. So this connection with the equivalence of. I'm sorry. Any question there?
Muna, did you ask something?
There are some.
Sorry, sir. Yeah.
Okay. So right. So this connection with the equivalence filter operator actually help us to utilize the results of Koenig and Stauber to apply that in our setting. So just to recall, Koenig and Stauber introduced this symbol class in equivalence setting, which contains all functions, which doesn't have any regularities on the space variable, but satisfy this kind of inequality on the dual variable. And they showed that for rho equal to 1 and A belongs to SM rho infinity for m less than 0, this is the associated systems operator is LP bounded for P belongs to 1, infinity. And now coming back to inner setting, since we know for each P, our symbol has to be holomorphic on the space on the strip SP, we define this SM rho infinity SP for 1 less than P less than infinity, which contains all such symbols from sigma from the function G cross SP union I gamma into C. For each lambda belongs to SP union I gamma n, the function x goes to sigma x lambda is Ky invariant and measurable on G and is bounded with respect to G and the I gamma n variable, while gamma is a finite number depending on n. And for each x belongs to G, the functions lambda goes to sigma x lambda is an even holomorphic function SP0 and satisfying these differential inequalities. So here also, we didn't assume any regularity condition on the space variable. Then we prove for P belongs to 1, 2, 2 infinity, and m less than 0, if we take symbol from SM1 infinity SP, then the associated systems operator psi sigma is a bounded operator from LPGN into itself. So in this result, we didn't use any regularity condition on the space variable, and we also produced some examples which belongs to this symbol class here. Okay. Now, since I have few minutes left, so let me briefly tell you some open problems or the problems that I've done. So instead of NN type function, you can also consider LN type function, where L may not be not equal to N, and define multiplier operator there, or Schirin's operator. And you can study this boundedness property of such operators. But what I can tell you is that the analysis of the global part and the discrete part, we are able to prove the boundedness property of the global and discrete part. What is problematic is that the local analysis of the local part. So the same method that we use to study local part will not work in the LN setting. And as in the case, as you saw, this we couldn't prove this for P equal to 2 case. So we are interested in the L2 boundedness of Schirin's operator, both in this setting and the symmetric space of non-compact type. And unfortunately, we got some results on the L2 boundedness on the symmetric space as well as harmonic in a group, but we are writing on this. Okay, and with this, so let me give you some reference for my talk here. So this is the anchor paper on the Hormeyer-Mill multiplier theorem on the non-compact types, and these are the reference for the representation theory on SL2R. And this is the results on Camporossi, who defines spherical Fourier on homogeneous vector boundedness over general Riemann symmetric space. And this is the Stein and Clark paper. This is the Anescu paper, and this is the Strobach and Koenig paper from which we stated the rough symbol class. And this is the multiplier operator paper from which our Schirin's operator is inspired. And this is the paper, this is the article on the archive from which all our results are borrowed. And we also studied this problem on the homogeneous tree setting, which is the discrete version of the hyperbolic spaces, just like in discrete version of R is Z here. And there in the homogeneous tree, what we got is that direct relation with the Schirin's operator on Z. But in this our case, we get a connection with the equivalent Schirin's operator. And with this, I'd like to end my talk. Thank you very much.
Yeah, thank you very much for a very interesting talk.
Thank you, boys.
Are there some questions?
Yeah, I have some question. Actually, I missed this last question.
Huh?
The last part. So can you read the last result actually which you are taking?
This one?
Yeah, this. This result and the previous result. Can you?
This one?
Yeah, yeah. Okay. What is the difference between this and this? Actually, I missed that last part.
No, here I just recall the result of Koenig and Strobach on the equivalence setting. What the equivalence setting. So where they define the symbol class there and prove the boundedness property of Schirin's operator in that for symbol belonging to the symbol class SM row infinity. And in this setting, we define symbol class here, and we showed that if take sigma belongs to SM1 infinity and m less than 0, then the Sirun's operator is bound operator from LPGN into itself. We also handle the p equal to 1 case, but to define symbol class for p equal to 1, we need to be careful with the n. For n belongs to odd number and n belongs to even number, we need to introduce some more notation. That's why I avoided it. But yeah, we got some result for p equal to 1 case too.
You can also take row equal to 1 here. I mean, row any row here.
Yeah,
row infinity.
Yeah. If you take any row, the problem with that with the local part again.
So there is a problem.
Yeah. If you take a general row here, so when you are writing like this, so remember the calculation, the local part. So if you take row less than 1, so that means you are taking less decay on the symbol variable.
Yeah.
Right. Then this analysis will fall up. This analysis is very very sharp in the sense that if you take less decay on the symbol variable, you will not get such. You cannot handle the k naught part. You may be handle this k error part, but you'll trouble handling this k naught part. I think so. We need a different analysis for that, because eventually we will be using this integration by parts, and things has to be exactly perfect to to prove this kind of estimate. But I'm not sure. I'm not saying it won't happen, but I couldn't do it in a mathematical way, so I avoided it. Anyway, in the equivalent part, this is your. If you take row equal to, if you take row less than equal to 1, you're not getting full p. So if you take row less than 1, you'll take the range of p from 2 to infinity. So I want to get for all p, that's why I take row equal to 1 to get the boundedness for all p belongs to 1 to infinity.
Oh, here also, if you take any row strictly less than 1, you don't get the full range.
Yes.
And I have one more question. This lemma which you have proved that psi I comma m mn belongs to weak LP or something, right?
Yes.
So how does one prove that? You have estimates for those things? And
so
for this,
what I did is that during my Wiener-Tauberin theorem, I studied this discrete representation theory and explicit. So since these are NN type or MN type function, it is enough to know the behavior of psi ik mn on of AT, that how psi ik mn AT behaves like. So from that sharp estimate of psi mn k AT and some you could say I use the estimate of psi mn k AT to prove this boundedness property. Because this MN type, you can play with the pattern decomposition. That's it.
You didn't conclude about one. The result you have proved this is for 1 less than p less than infinity, the which you have the boundedness of LP multiplier. But the thing is,
in the case of multiplier here, they didn't prove the they didn't say anything about p equal to 1 case. They avoided that. This also the same problem with the local part.
Even weak L1 we cannot say.
No, weak L1 they didn't prove, because what they did is that this trick is hide in this part. So here, when you are taking p greater than 1 or even p equal to 1, you can dominate this by using Minkowski inequality. You can dominate this local part of this as this operator. But when you want to prove that, this is very too much to expect that this local part will be a strong L11. So what you want to do, you want to estimate the weak type 1,1 norm of psi log sigma f. And what happens problem is that you don't have the weak type version of Minkowski inequality. So we cannot dominate this high sigma log of weak type L1 norm as this kind of function. But I think Fulberici, that's why they also didn't try to prove the weak type 1,1, because I also faced the same problem.
Actually, okay, so I have two more questions. So one thing is this Stein's thing, actually, you have quoted that, okay, in the first result. So for
Stain,
LP
Euclidean setting.
stain. No. So this is so symmetric space. So it was symmetric space setting. So this for boundedness of LP multiplier. So you are really assuming that the means all the derivatives of m lambda okay is bounded inside the interior.
Yeah.
But the thing is, I'm just curious to know, can it be extended to be this means continuously this multiplier to this whole strip? But the Ionescu result is still gives some kind of contradiction.
Ionescu doesn't say anything about the function
Yeah,
itself. What is saying the derivative can have allowed to have singularity as this plus minus IOP. But like if you like, why you want to extend this to the external boundary? Like, what is the benefit of that?
No, actually, that is the thing that this Ionescu result actually says that it is not really needed that it may have singularity at boundary, right?
Yes.
But the thing is, Stein's thing actually probably I'm guess Stein's thing says that derivatives are uniformly bounded. So I had an impression that probably you can extend
Stein is not saying they are not saying anything about the derivatives of that. They are saying that the multiplier itself is holomorphic and bounded there.
AM extensions are sorry. Derivatives are not uniform. I missed this point.
Yeah. Okay.
Oh, so derivatives are not okay.
Yeah, they are not saying anything about derivatives. They are saying the multiplier itself.
Okay,
just like in the Euclidean setting, you know
no. That was really Kajikanza. Yes. Now I understand.
Just like in the Euclidean setting, so here the multiplier has to be bounded to be L2 bounded because it's a necessary condition too. Because the norm of L2 norm of Tm is sup norm of M. So if you don't assume M is bounded, Tm is blows up. But you don't need you don't need this bounded condition on the derivative of the multiplier. It can have singularity as I equal to 0.
Okay? Actually, another small question, very trivial question. So for multiplier operator, if it is something is LP bounded, then you know that this is LP prime bounded, right?
Yeah.
But the thing is, does it happen? But no. Does it happen here? No.
No. For students operator, so this what happens is that for multiplier operator you can write as a convolution operator, and then by by duality you can simply change P prime. So so what happens in the multiplier case, they only study 1 less than P less than 2, and then by duality they extend it for P greater than 2. But for students operator, since you cannot write as a convolution operator, so you cannot use such duality argument here. So, so for P greater than 2 and P less than 2, there are different analysis. We have to do the analysis by hand.
Okay, I don't have any.
But I think it is true in the Euclidean case, right?
Yes. For any almost any multiplier case in any setting, it is they do
I'm
this
saying
like
even the pseudo multipliers in the symbol class, if you take the adjoint of it is going to be again a pseudo multiplier, right?
Yeah. For Euclidean case, they do that. But in this case, we don't know whether adjoint of a student's operator will be again.
The symbol calculus is not yet understood completely.
Yes.
I have one or two more questions which are kind of like not because I missed some part of your talk. Anyway, so the question is like, as you have said about the weak type 1 thing, did you try the local Hardy spaces and things like that?
No. But I have planned to. But I want
you can try.
Yeah.
And also, I think even with the Koenig-Stobach thing, one cannot expect the M to be 0, right? When rho is 1, one cannot expect M to be 0 because you cannot include the Calderon-Biancourt theorem, I guess.
No. You cannot. Yeah. You should not expect M to be 0.
Okay. Yeah. Okay. Thank you.
Okay. Thank you.
Yeah, I guess there are no more questions. Yeah. Thank you, Tapendu, once again.
Yeah, thank you.
So let us stop the recording.
Yeah. Bye.
Bye.